camera. We're good? Alright, so what are we doing today, I guess? If this is a talk about things that look like Ramsey theorems or anti-Ramsey theorems, I should remind you what Ramsey's theorem looks like. So here's probably its most basic form. Ramsey. Let's say K and R be natural numbers. I use omega sometimes to write like the set of natural numbers because I'm a logician. So what I'm going to write is going to look kind of funny, but I'll explain. So the statement, omega arrows, omega K R is true. So this is a statement. What does it say? So the statement omega arrows omega K R says that for any coloring gamma is going to color the k-tuples of omega in R many colors then there is an infinite a subset of omega. So this infinite subset corresponds to this part of the notation, the notation inside the parentheses. So that gamma restricted to the k-tuples which come from A is monochromatic. So monochromatic just means that the image of these k-tuples under gamma, they all fall in one of these color classes. So that image has size singleton. So then, now this theorem makes sense because it is saying that this statement is true. Let's think about the case, the first non-trivial case is probably k equals R equals 2. So let's very quickly sketch for k equals R equals 2. So we have a coloring of pairs into two colors. So we're splitting up all the pairs into two classes.
Are these ordered pairs?
You can. Yeah, so I mean since omega has a natural ordering on it, just take the pair in that order.
Okay.
So here is let's think about 0. Here's 0. So 0, let's say that the colors are blue and red, because I have those readily available. So the 0 sees some blue edges emanating out of it, and 0 also sees some red edges emanating out of it. At least one of these two sets, we can think of this as we just partitioned the other the remaining natural numbers into these two pieces. One of these has to be infinite. So without loss, say that the red piece was infinite. Log red piece infinite. What I'm going to do is I'm going to just throw away everything that had to do with the blue piece. that's just gone now. So we just deleted a whole bunch of natural numbers, and now we only have this red piece. Now, so say I might have deleted 1, I might have deleted 2, so on. At some point I have the least entry, maybe I'll call this like N1, that survived the first operation. And I'm going to do the same thing with the remaining survivors. N1, so this is stuck being red because 0 thinks everything is red now. So N1 is going to do the same thing. N1 sees some red edges and N1 sees some blue edges. Same thing. One of the pieces has to be infinite. This time, let's just say the blue piece was infinite. Once again, I'm going to just delete anything that had to do with N1 thinking that things were red. Except, of course, 0. 0 already happened. And then I keep going. What happens at the end, I obtain a subset B, let's call it. It's not quite A yet. So that if B0, B1 are in B, gamma B0, let's say B0 is less than B1, the color of this pair only depends on the least entry. Right, because that's exactly what this pruning operation did. We sort of got rid of all of the ways that this could not be true. And so now of the survivors, so we have, so 0 survived, this N1 survived, there was an N2 that survived. So 0 thought that everything going forward was red. N1 thought that everything going forward was blue. N2 is going to have some sort of opinion, etc. Some infinite number of members of B will have the same opinion. And I'm going to pass to that subset. So I'm just going to write very quickly. Pass to A, subset of B, so everything has the same opinion. So for more colors, the proof would be almost exactly the same. For higher order of tuples, you have to run induction. So this would be the case for k equals 2. You prove k equals 3 using the k equals 2 result, so on. So I just want to place this in your mind so that we can start thinking about if it's possible to strengthen Ramsey's theorem in certain ways. And there are tons of generalizations of Ramsey's theorem. There's this theorem called the Erdős-Rado theorem, where I'm coloring the pairs from huge uncountable sets, and I want like an uncountable clique all in one color. There are generalizations where instead of a natural number here, I'm looking at all the infinite subsets of omega, and then you're asking for colorings which are quote unquote definable in some way. So there are theorems by Devlin and Trickery, and then later Ellentuck on that front. So I'm going to be talking about what's known as structural Ramsey theory. So the Ramsey theory of, I guess, countable first order structures. And we're only going to be talking about one such structure today. We're going to be talking about Q. So what is Q? Q order, which from here on out I'm just going to write Q. This is just here's kind of a circuitous definition of what this is. The countable dense linear order. a more model theoretic definition. If you want something concrete, it's literally just the rationals. Think about the rationals with their linear order. But I don't care about addition or multiplication or anything like that. Just the linear order. That's the only structure I'm interested in. So let's consider the following scenario. Say that I had coloring from the pairs of rationals to 2. So this is a coloring. So Ramsey's theorem tells us something. So Ramsey's theorem, there is some infinite A subset of Q, so that all the pairs are monochromatic. It's monochromatic under gamma. I'm going to start calling this, I'm going to say just that A is monochromatic for gamma when the size of tuple is understood. But now, you might think, now that there's this structure floating around, various infinite subsets of Q are not created equal. Like, what do I mean by that? So here's Q. One infinite subset might look like integers, so I can just have the integers floating around. I can think about maybe I have the rationals between 0 and 1. Maybe I have some dense, codense subset of Q. So this linear ordering introduces a lot of structure that infinite subsets of Q might have. And so it's interesting to ask, how does Ramsey's theorem interact with that structure? So here's the sort of the definition I'm going to be focusing on. Call A, or let me, this definition is in 2 stages. MQ is the set of order-preserving injections So you can think about, if I have such an injection, you can think about the image as picking out a copy of Q inside of Q, and sometimes I'm going to use that language. And then here's the notion of infinite subset I'm interested in. A set, a subset of Q is large if there is some embedding whose image is contained inside A. So for instance, with that that Q line I had drawn before, the integers are not a large set. The integers do not contain a copy of an order isomorphic copy of Q inside. The rationals between 0 and 1 is a copy of Q. So that's going to be large. Copies can look kind of weird. Like maybe I take like all of the rationals below root 2, and then 5, and then all of the rationals above 17 pi. That's a good copy of Q. That is an order, that is a linear order isomorphic to Q. Because I have something that looks like this, no endpoint, some random point, no endpoint stuff. That's just fine as well. So copies of Q inside Q, I'm not saying anything about how the copy sits inside Q. I'm just saying that with the ordering it inherits from Q, it looks like a dense linear ordering without endpoints. So I'm going to write, Q arrows Q to 2 for the statement. So I'm not even going to write this down, but so the notation is pretty suggestive. What is this saying? This is the statement that if I take any two coloring of the pairs of rationals, that there is some large subset of Q whose pairs are monochromatic. So not just any old infinite subset, but a large subset. So this is just a statement. I didn't tell you whether it was true or false. It's a false statement.
So large means it contains a copy of
Contains a copy. Doesn't have to exactly be a copy.
Yeah.
So like a interval thing that's large.
Yeah.
So fact. Q does not arrow, and this is just the negation of that statement. Q does not arrow Q to 2. Let's prove it. Let's enumerate Q. I can think of this enumeration gives us a new linear order less than, I should have given this enumeration a name. Maybe I'll call it less than overscore thing. Yeah, it's a notation. We have a new linear order where I'm actually going to give this enumeration a name. So it's like phi. It goes from Q to omega. So the pre-image of n is a. So phi inverse n is a. So it has a name. So now I'm going to give this is just order phi, where p is order phi less than q. If and only if phi of p is less than phi of q. So if p was enumerated before q was enumerated. So now every pair has two competing linear orders floating around on it. There's the normal rational order, and there's this new enumeration order. And that's going to give us a color. Color, the pair PQ, depending on whether, so I have rational order, I have enumeration, agree or disagree. So I just want to make sure it's clear that this works to give us a two coloring. Every pair is going to have some sort of opinion. So the claim is that, and let me actually give this, let me call this coloring gamma. claim no large subset of Q is monochromatic for gamma. So how do we prove this claim? Well, intuitively, what's going on, anything that looks like a copy of Q is going to have infinite rational descending chains and infinite rational ascending chains. That's going to be a problem trying to get everything to look like this well order. So that's going to be a problem. So say, let's say that eta is an embedding. Then an order phi restricted to the image of eta still looks like order type, or maybe I'll just say still looks like an enumeration. I can consider the least element of the image, which was enumerated by phi, and then the next least, and so on. So this still looks like an enumeration, and an enumeration I can't enumerate the rationals in order or descending order. So I can't enumerate rationals by only ascending or descending. Ascending or only descending. So this is kind of cool. This gets at the heart of what I mean by anti-Ramsey phenomenon. So Ramsey phenomenon refers to finding structure no matter how I try to partition some sort of underlying structure. Anti-Ramsey exhibits a partition which destroys all the structure. So we've destroyed every copy of Q inside Q by using this coloring.
So this proof shows that you can't even have Z embedded inside.
Yeah, you can't have Z, you can't. Yeah, so this gives you a lot more information on like which order types are admissible. Yeah, in fact, they have to look like well orders in one direction or the other. So, let me just make a few remarks. So remark is due to Devlin, I want to say. This is the worst possible. I.e., what did Devlin prove? Devlin proved the statement. Devlin showed. So once again, I'm going to write down some cryptic thing with arrows and numbers everywhere, and then just explain what it means. Q arrows Q 2 3 2. What on earth is this? I.e. If gamma from the pairs to 3 is a coloring. So this 2 is this 2, this 3 is this 3. What is that? There's a new 2 out here. What is this saying? Is a coloring. Then there is a large A subset of Q So that gamma, the image of a squared under gamma has size less than or equal to 2. So I can't get down to one color, but I can get down to only 2 colors, even though I started off with 3 colors. In fact, his result is stronger. It was true for any k. So if k is any finite number, I start off with a k coloring. I can always avoid all but 2 of them. It's really weird. So we have anti-Ramsey theorem, but not by much. Like up to a point, Ramsey sort of takes over again.
So can you just repeat that slowly for me? So you color the pairs
Of rationals.
and then you can find a large subset where the pairs are one of 2 colors rather than just monochromatic.
Yes, exactly.
Got it. Thanks.
Now, it's like really bizarre. Why is this theorem true? It's weird. I think I gave a GSS talk in the past discussing this theorem just for 2 colors. Like it's actually tricky even in this case to prove it. What I'm about to write down is very difficult to prove the upper bounds. We're going to focus on the lower bounds today. So here, after much waiting, is Devlin's theorem. There are numbers tk. Actually, no, let me even be more precise. It's not just that there are numbers, like he told us exactly what they were. Let tk, I'm going to define this more precisely later, but for those of you who might know this definition, these are going to be the odd tangent numbers. Odd tangent numbers. Then, tk is the, or actually I'll just write it this way. Then the following 2 statements are true. Q, arrows, Q, K, R, TK, for R greater than TK, or I guess greater than or equal to. So R is some large finite number of colors. And Q does not arrow Q, K, R, TK minus 1. So what does this mean? Let's go through it in words. So when k is equal to 2, t of k is equal to 2. So that tells us that I found a bad 2 coloring of the pairs, but for any larger number of colors, I can always get down to 2 colors. This says the same thing with 2 replaced by tk. There are bad tk colorings of the k-tuples, that's what this says. But if I try to color with any more colors, I can always get down to tk many colors.
So the odd tangent numbers are tangent numbers that are odd or weird. What the odd tangent numbers are.
Yes, I'm about to say what these are. They're not just weird numbers. The odd actually refers to parity.
2 isn't odd.
2 is not odd, but it refers to, it's discussing the generating function for tangents. So these are the coefficients on the odd degree polynomials. So just as a remark, this same, like, while I'm erasing, I shouldn't have erased it. So this same trick where I throw an enumeration on top and compare how the two orderings look, that works to give me a bad, so it gave us a bad 2 coloring of the pairs. It works to give a bad k factorial coloring of the k-tuples, because there are k factorial different ways any 2 linear orderings might compare to one another. Unfortunately, the tangent numbers grow a lot faster. So there are worse, sorry Joe, I'm sorry that you're sad. It's even worse than that. Let me actually describe what these numbers look like, because it's really weird. Definition. Tk is equal to, or I'm going to say Tn is equal to Tn minus 1. Tnk is defined recursively. Oh, and I think I took a picture of my whiteboard on my phone. Like a true mathematician.
I'm just going to show it to us.
No photos. What? Oh, did it not save the, oh, I don't think I saved the photo. 1 second. Oh, and I don't like iOS 10. Alright, we're gonna work through this together. Here it is. I had to unlock my phone. Alright. Tn 0 equals n factorial. Tn equals 0. Oh yeah, so I guess it's only defined when k is less than or equal to n. Tn k, actually I'll write it this way, Tn plus 1 k plus 1 is equal to n minus k times Tn plus 1 k plus Tn k plus 1. So it's not growing crazy fast. This is primitive recursive, but it's fast. It's faster than factorial. Let's draw the first few steps in this recursion. I'm gonna grab my picture. All right, here we go. Only draw it up to 5 because you'll see it grows very fast. Alright. So what's our base case? N0, I guess we could say. So just factorial. I don't care what's going on below here. Zeros down the diagonal. And then I use this kind of funny looking recursion. My phone keeps going to sleep on me. Alright. 2, 16, 16, 120, 272, 272, 960, 3,696, 7,936, 7,036. So, if we really wanted to, we could construct a 7,936 coloring of the 5 tuples of rationals so that each color class was unavoidable, but each color class hits every large set, but that's the worst possible. Just why is this theorem true? I don't know. So So I'm going to focus on maybe not this end of the triangle, but maybe this end of the triangle. I want to exhibit this 16 coloring. 16 is a bit,
One or something. I thought you were going to focus on like one.
that would be a little bit too extreme. So yeah, how do we get a 16 coloring, which is pathological? We're going to have to, it's going to be motivated by this enumeration trick, but we're going to have to work a little harder. But the good news is that once we construct the 16 coloring, we will actually have constructed all of these colorings for every single K. So what we're going to do is our colors are going to be certain structures, and we're going to be adding structure on top of the rationals. So it's a little bit easier to think about all the structures that might look like this, rather than just 7,000 random colors. Construct a 16 coloring of triples. So we are going to enumerate the rationals. Enumerate 5 q to omega, where I'm going to call a n is the element of q with 5an equals n. An is the nth element we enumerated. Now I have to parse through this jumble of notes, because as it turns out, it's kind of finicky to get this construction right. So I had to go through a few iterations, like yesterday and today, to actually make it correct. So we're going to use this enumeration in kind of sneaky ways. So what we're going to do is we're going to define the following wedge operation. Define wedge. Wedge is going to go from Q cross Q to Q via, let's say that P wedge Q equals R if R is the phi least element of the closed interval. I'm going to just assume that P is less than Q, less than or equal to Q. So in particular, if P equals Q, then the wedge just returns P again. Otherwise, I actually have some non-trivial amount of interval here, and I just search for the least enumerated element of this interval. So somehow, tuples are going to, using this wedge, tuples are going to remember more about where they are in the enumeration than just the phi order would tell them. They're going to remember things about how the enumeration looks in their interval. That's how we're going to get more colors than just 6. But we don't want to remember all of wedge. So now I've defined wedge, I'm going to tell you exactly how much of wedge we want to remember.
Can you recover phi from wedge?
Can I recover phi
so from knowing P wedge Q for P and Q, can you tell which of P and Q is least with respect to phi?
You would say I don't think you can. I mean, you probably can from wedge. It's a little bit weird. But with this next thing, you will be able to recover phi. So instead of using.
Yeah, never mind. I answered the question in my head. So
Okay.
go on.
I think the answer is yes. So we're going to, so for the 2 coloring, we introduce this new ordering, order phi, which just recorded the enumeration order, and we were fine. Instead of linear order, we're going to have to get a little bit fancier. We're going to introduce a ternary operation, or no, not operation, relation, R, and I need to tell you when R, P, Q, R holds, if and only if, let's see, I want P less than or equal to Q, and either, and I should say, and one of these cases are mutually exclusive. So I calculate the wedge of P and Q and ask if it was enumerated before R was. If that's true, I declare this to hold. The other situation is that P is strictly less than Q, and P wedge Q actually just equals R. Then I'm also going to declare R to hold. It's useful, I'm gonna say something that might sound kind of cryptic now, but will hopefully make more sense in a little bit. It's useful to think about this in a way so that there aren't any ties. That's what I mean by that. So if P wedge Q equals R, it's helpful to think about P wedge Q as actually being some element in like, not rationals, but like extended rationals that is like infinitesimally less than R. So here's R. So think of P wedge Q as not being R per se, but just being like infinitely less than R. Or no, not infinitely less, just very, very little less than. Similarly, it's helpful if P wedge Q is equal to, so say that here's P, here's Q, say that P wedge Q is equal to P, like P was the least enumerated in the closed interval. Then it's helpful to think of P wedge Q as being just a tiny bit greater than P. So again, these remarks might seem kind of cryptic, but it's going to be helpful to think about how we break these ties. Alright. And with this we have our coloring. So what is the coloring? So now the color of a, I'm going to erase this bit just so I can write here. So now, color a tuple. Based on its structure, inherited in Q with its standard rational order and this wacky relation. So does this, I want to make sure that this makes sense as some sort of coloring. It shouldn't be clear how many colors there are. It shouldn't be clear that each of the color classes is going to be unavoidable, but we've yet to prove those things. It should be clear that there's only finitely many possibilities. Just because this is a binary relation, this is a ternary relation, there's only finitely many ways I can cook up a structure using these symbols on a set of size 3. So this does give us some finite coloring of rationals.
Is it possible for both those things to hold? Is it possible for both of those things to hold?
For
the same?
both 1 and 2?
It's not going to.
It shouldn't be possible because
Okay.
the moment this holds, then
Yeah.
you have strict equality here. Yeah, so either strict inequality or p is less than q and equal. So they're exclusive. So the claim, the first thing I'm going to prove is that this is an unavoidable coloring. This coloring is unavoidable. And I guess I never defined it. I just want to make sure. Is it clear what I mean when I say unavoidable? So unavoidable colorings are these anti-Ramsey colorings.
Is this a coloring that you're going to define, or should we just understand that there is one?
The coloring is this structure. I've taken a triple and I've colored it based on the extra structure it gained in this.
We're coloring it in how many colors? 16?
It's not clear yet that it's 16, but it will be 16.
Oh. So based on the truth values of the
relation
of
R.
of the relation R.
Because this is just the standard rational order. That's the same for every triple.
Yeah.
Yeah. So the coloring of a triple is going to be coded by what R does.
Coded by what R does.
Mm.
Okay, sure. I'll believe you.
So fix a large set S, goes to the Q. It will suffice to find an embedding maybe eta. Eta is going to embed this whole extended structure into itself. Yeah, I should be clear what I mean by embedding. My embedding, so like this is an embedding of models, so it's an injective map. It preserves the relations, it preserves the non-relations. So an embedding whose image is contained inside with im eta. Subset of S. So why does that make it clear? Why does that make it that this coloring is unavoidable? Well, here's a large set. I found a substructure isomorphic to the whole thing inside of S. So it's going to see all of the possible structures on triples in particular because it sees the whole thing. So if I'm able to do this, I've shown that all of the extra structures I put on triples, they really are unavoidable. They see every large set. Oh, I kind of want to leave up this. I'm going to leave up this diagram because I might not have time to do what I want to do with that diagram. So what's the procedure? So we're going to inductively create a function f from omega to omega, strictly increasing. Or I guess not strictly increasing. What do I want? I don't require f of n to be greater than n. I require f of n plus 1 to be greater than f of n. I'll just write that down. With f0 f1 less than, etc. So that the map eta is going to send q to q given by eta of, oh, I should have said something, Hey, and I'll say it later. N equals A f of n is the desired embedding. So this is just some enumeration, but I wanted to say, let's assume, we will assume that this enumeration is the phi enumeration, that phi of an equals n. So not just any enumeration, this particular enumeration that was used to define the relation R, all of that jazz. Oh, there's so many things I want to leave on the board. I'm going to erase the grid numbers.
You can slide
Oh,
the
yeah,
board across.
slidable.
But once you start sliding, then you have to like slide and unslide, and I just want to.
Well, it's reversible, right? But erasing is not.
I'll take my chances. Okay. So we're also going to inductively, at each stage, we'll have this set S. S was our large set that we started with, is going to be partitioned into order intervals. So at each stage, let's say that the stage was called K, or I think, no, I called my stage J. At each stage J, I'm going to have intervals ij 0 less than I mean, really I'm saying S is the union of these things, but these intervals are like, here's an interval and here's the next interval, so they're in order in this way. J1 all the way up to I, J, J. These intervals are in some sense going to be determined. So notice there are J plus 1 pieces at stage J. The idea is going to be that we're going to have, like say that I had, J was 3. So I've laid down 3 points so far, and that splits things. There are 4 regions I'm interested, determined by where I'm looking relative to these 3 points I put down. So how do we start? So set f of 0 equal to the min n such that the phi preimage of n is in S. And so this makes sense, right? S is some subset of Q, so it's going to correspond to some subset of the enumeration. This is just to be phi at least 1. So let me draw a picture. So this is going to be AF0. Now, consider the collection of AI for I less than F0. These are going to pose problems if we're not careful with them, because R was defined in terms of this meet operator, but our embedding, even though we can have our embedding play nice with respect to the rational order and the phi order, it's not going to necessarily play nice with the meet operator, because that's extra knowledge. That's like kind of forbidden knowledge. So if we're not careful with where these are, we're going to screw up in getting R to work. So the strategy is I'm going to sort of define F so that I get an embedding. It'll be clearly an embedding of the structure with the rational order and the phi order, and then we have to spend a little bit of time to convince ourselves that it works for the R relation as well. So what is this set? So there's going to be some of these might be down here, some of these might be up here. They're problems. So like maybe this was A0, here's A1, who knows, A2, A3, A4. And this splits everything into pieces. In particular, so notice that both S and S less than AF0 and S in S greater than AF0 are large. Why are they large? Because AF0 is in S, and S looks like, oh, I should be careful, I should be really careful. I'm not going to fix any large set. I'm going to call S actually the image. Fix A, it's actually going to be a copy. Does that distinction make sense? I really just want to zoom in on the part of S that looks like a yellow, so that I can say this. So these are both large, and I've split up these AIs split up each of these large set into finitely many pieces. So largeness is nice in that it's indivisible. So this anti-Ramsey phenomenon that showed up for the pairs does not show up for the singletons. The singletons are indivisible. So if I try to split up a large set of singletons into pieces, one of the sets has to be large. So in particular, I can choose intervals. So this is how I'm going to define I, 1, 0, I, 1, 1, to sit inside these intervals. I'm not being very precise. Also, this is not equality, this is just containment. But each of these meets S in a large set. So I0 might be something like the members of S strictly between A3 and A0 or something. I1 might be members of S strictly between A1 and A2. The idea is that it would be a shame if in the image 2 points want to calculate their meet, and it's supposed to be something different, but wait, we forgot that A0, like our embedding, forgot where A0 was, and now Wedge wants to say it's A0, but it can't be A0 because it's not there. So you have to be kind of careful. So hopefully my ramblings are making sense.
Can I ask something about S?
Yes.
You said fix a copy. Any copy?
Any copy.
Why not just Q?
No, it's handed to you adversarially.
Okay, oh, okay, right. Okay.
So someone hands you a copy.
Okay, I get it, yes. Gotcha.
Alright, so what's, I'll maybe do one more step of this construction and then say ... So what's the next step of the construction? Yeah, because we're also running low on time and I don't want to take up too much time. So next step, say log that A0 was less than A1. So what this tells us is that we're going to be paying attention to I1 water. We want to pick our next guy to be greater than A of F0 so that that's an embedding. And I'm just going to set F of 1 to equal min n, so that phi inverse of n is in S intersect I11. And so if A1 were less than A0, I would be interested in I10, for instance. I should label these on my diagram. So let's say that I've done this. So here is A of F1, let's say. Sorry, this is getting crowded. But so this is A of F1. And now we have the same issue. There are points that we skipped which are going to mess up the computation of wedge. So now we have to consider all of those AI with I less than F1. So there's more things going awry. So maybe I missed points in here that's going to split up I10, and points in here, and points in here. So same sort of thing. I'm going to pick just one of these intervals to become, this will become the new, so this interval might become I20. I11 is going to be split up into two pieces, because there's going to be the piece less than AF1 and the piece greater than AF1. And once again, I'm going to make them small enough to be inside one of these intervals that was determined by these pathological people. So without going into the gory details, this continues for omega many steps, and ... it works. I don't have time, unfortunately. I wanna convince you that there are actually 16 colors. So let me spend the last 5 minutes or so convincing you that there are 16 colors. So why 16? So we can think of what's going on is as follows. So say I have a triple, A, B, C. I also have, here's A meet B, here's B meet C. Where does A meet C? Notice that A meet C has to be one of these, because this was the least enumerated thing in this closed interval, this is the least enumerated thing in this closed interval, so one of these has to be the least enumerated thing in this interval. So I have these 5 points, and I can ask in what order were they enumerated. But I know that I can't just pick any enumeration. I know, for instance, A wedge B had to happen before A. Similarly, B wedge C had to happen before B. So what we're going to count enumerations. With, let's see, A wedge B before A and B, B wedge C before B and C. And so this is why I was mentioning earlier, it's useful to know how to handle ties, or to have a convention regarding tie breaks, so that you can always just think of it in this sort of there's a strict ordering to what's going on. So let's write down these orderings. Well, I can certainly put all the wedgy things before any of the non-wedgy things. So there's I can rearrange those in 6 possible ways. I can rearrange these in 2 possible ways, so that's 12. I can do A wedge B, and then I'm free to write down A. Then I have to write down B wedge C, then I can write down B and C. 2 ways to rearrange those. And then similarly I can write down C wedge D. I can write down, well not D, B wedge C. I can write down C, A wedge B, and A, B. That's 2 of them. That's 2. This is 16. Alright, I think that's all I have time for. So, Devlin's theorem, weird.
So, any questions or comments?
Can you just repeat what we were proving? What Devlin's theorem was? Just
So what did we do? We just proved that there is a 16 coloring of the triples, so that in any large subset, the set of colors you see on that large subset's triples is all of the colors.
Okay.
Yes.
Can you give an idea of how these things accounted for higher uniformities to get the tangent numbers?
Oh, like how do you get 272?
Yeah.
Well, I have.
List them.
I can actually list them. That's what's cool. So it's intimately related with the Catalan numbers. So here is what I was hoping to do if I had more time, which I don't. But that triangle I drew with numbers, you can think about paths through that triangle staying above the diagonal, and that's exactly what Catalan numbers are counting. But now we have this sort of weird multiplier effect. So a path that looks like going all over then all down is like putting all of your wedges first and then your non-wedges. A path that sort of goes over for a few and then drops down, that's having some wedges and then some non-wedges and then some more wedges, etc. So like there's a bijective proof if you follow that.
So you are implying in the higher cases, so it's just enough to have the branch and
Yeah, so this structure actually works for all K. Yes?
So were these numbers introduced for this theorem, or
No, they're the odd tangent numbers because tangent of here is where these numbers first came to light. The sum from n equals 1 to infinity of t n x to n minus 1, I want to say. So if there's some like deeper connection between like partition properties of the rationals and the actual tangent function, that would be really weird. I'm not convinced. Like it's just like the same like recurrence relation, but yeah, it's weird.
let's again.